Today I will speak about Anderson localization of light from random to aperiodic systems. Okay, so I will begin with a brief overview on Anderson localization for the condensed matter, and then I will also speak about Anderson localization of light and classical waves. And finally, I will talk about my work on localization of light in periodic metamaterials, including aperiodic ones. Well, to begin with, let's discuss wave propagation in general. It's a very common effect in nature. So it involves light propagation in clouds, in astronomical systems, in glass of milk or beer, and also in condensed matter. It deals with the propagation of electrons in a copper wire, and it is very well known that this effect can be described by the diffusion equation that is here. And if you calculate the mean square displacement, this will be proportional to the diffusion constant, which is related to the energy transport velocity in the medium, and also the mean free path. The mean free path is the important length scale here that will give an average distance between two scattering events, right? And well, this occurs for every kind of wave. So let me begin with by introducing the concept of Anderson localization. So this is Anderson. This is the subject that has given his Nobel Prize in '77, and the idea here is that if one has, right, a copper wire, for instance, with some impurities inside, and the electronic wave function propagates throughout the sample, and if the concentration of impurities is low enough and the temperature is high, we have a metal, we have a conductor. However, if one increases the density of impurities and also decreases the temperature, eventually the electronic wave function due to interference effect may be localized due to multiple scattering inside this sample, and the system may undergo a phase transition between the metal and the insulator, and this shows up as exponential decay of the current, and the characteristic decay length will be the localization length, right? That it's very important to describe this phenomenon. Okay, and oops, I'm sorry. Let me share again. Okay, and this is actually the subject of this very famous paper by Anderson in '58, okay, which is the absence of diffusion in certain random lattices, right? So this all occurs in 3D only, right? This metal insulator transition. And in this same paper, he introduced this very well known Anderson model, which is based on a random displacements of the potential. So whenever you have periodic potential, you have an extended wave function. However, if one introduces this randomness in the potential, eventually the propagation of the electronic wave function may be localized exponentially, and this will show up as a exponential decrease of conductance in a random medium. Okay, so this is a very interesting quote by Anderson in his Nobel lecture in '77. So he stated that localization, that very few believed it at the time, and even fewer saw its importance. Among those who failed was certainly its author, Anderson, and it has yet to receive an adequate mathematical treatment, and one has to resort to the indignity of numerical simulations to settle even the simplest questions about it, right? So probably I will speak about some indignities that I have committed throughout my career, but this is the way that we an important way to treat Anderson localization, and we'll discuss a lot of numerical simulations here. Okay, but this another curious fact is that almost say 10 years after the publication of this famous 58 paper, it had only 30 citations, and now it is well known that it has 14,000 citations. It is used throughout different branches of physics, and even in '83, Anderson quoted his paper as his discovery as an unrecognizable monster. This is the image of Frankenstein, that even his inventor does not recognize his discovery, and because nowadays it has many manifestations, many applications in different ways that this effect can show up in different areas of physics, right? As I said, there are many manifestations of Anderson localization, or many disguises, if you wish, and one of them is the suppressed diffusion. So this is very hard to measure, right? So the mean square displacement will be a constant. This is very hard to probe experimentally, and also another important definition of Anderson localization is what we call the dense pure point spectrum. So this means that the system has no level repulsion if you investigate the spectrum. However, this is only in principle defined for a closed medium, but in practice, in an experiment, we have an open system, so this is also very difficult to measure, right? And another important manifestation is the fact that we have giant no-Gaussian fluctuations that is expected to be log normal. We have complex dynamics, complex behavior of transmission as a function of time, and there are predictions for this. And this is also an important contribution in the field of mesoscopic physics. So in order to probe localization, we need a good observable with continuous control parameters such as the system size, the energy, and the time, right? And of course, we need a good theory that allows for engineering, right? Okay, so let me discuss what we should call the great theoretical principles for Anderson localization, right? These are established approach, criteria for Anderson localization, and one of them is the Joff-Hegel criterion, which states that the wave number k and the mean free path L, this product is of the order of 1. So this means whenever the wavelength is comparable to the mean free path, one has localization, right? We can have interference by multiple scattering, and this can be the wave eventually is localized. Another important criterion is the Thouless one, right? That indeed compares two important time scales. The diffusion time, which is the typical time an excitation needs to be transported throughout the whole system of size L, and the Heisenberg time. The Heisenberg time here is the inverse of the mean level spacing, which is this quantity here, which is the smallest energy scale in the whole system, so that the Heisenberg time will be the largest energy scale in the system. So localization sets in whenever the diffusion time is larger than the Heisenberg time. So in this way, the wave cannot propagate throughout the sample, and the system is localized. Another very important contribution to Anderson localization is due to what we call the Gang of Four: Abrahams, Anderson, Ricciardello, and Ramakrishnan, who developed the scaling theory. This is very important for the experiments, because this deals with the sensitivity of the transport to the boundaries, to the system size. So this is very important for a very important criteria for Anderson localization in open systems. So it deals of how the system conductance evolves as one varies or increases the system size L. So one important conclusion of this scaling theory is that for low dimensional systems in 1D to T, all states are localized, right, in principle. But in 3D, one can have the metal insulator transition for critical disorder, and this behavior is captured here in the scaling function. I will talk more about this throughout the talk. Well, for electrons, it's very difficult to observe experimentally Anderson localization. Firstly, because interactions, electron-electron interactions, can also induce different metal insulator transitions, such as Mott transition. And experimentally, this is very difficult to achieve because we need a very low coherence length that it can only be achieved in very low temperatures. And also, however, there are important works in this field, for instance, of Bruskin, that established the connection between Anderson localization and the integer Hall effect, quantum Hall effect, and also confirms the scaling theory, right? However, in 1985, Anderson actually proposed it as since Anderson localization is essentially a wave phenomena, he proposed that this can occur for every kind of wave, light, ultrasound, even seismic waves. And he proposed what he called the theory of white paint. So this can be achieved in white paint. So the point is, why not use classical waves such as light to investigate Anderson localization? And advantages are that photons do not interact with each other. The experiments can be done at room temperature, and however, disadvantages are that localization at low frequencies is not possible. This is characteristic for light scattering, Rayleigh scattering, that is very weak, right? And also there is the problem of absorption that complicates the interpretation of the experiments, and this has been historically one of the major difficulties to confirm, to observe Anderson localization of light. Well, and based on this first idea of Anderson, I would like to quote this sentence by Léon Brillouin in his very good book of wave propagation periodic structures, that waves always behave in a similar way. So it can be quantum waves, matter waves, electromagnetic waves, waves in the sea, and even seismic waves, right? And when based on this quote, one can establish several a lot of analogies between quantum and classical waves. You can write a wave function, an eigenvalue equation that is similar, but one major difference is that if you write the potential for quantum waves, it does not depend of energy, whereas here we have a potential that depends of energy that has many important consequences. One of them is that the energy in the classical case, in the scalar classical case, will be always higher than the maximum fluctuations of the potential. So localization is very difficult to achieve for classical waves. Another important difference is that the conserved quantity will here contain this term, so which is not which has not an analogous in the quantum case, so that we can see that in dynamical situations, classical wave propagation will be expected to be different to the quantum case, right? So we can construct a table of analogous quantities between classical waves such as light and quantum waves. Okay, So now let me discuss some important historical achievements in the field of localization of classical waves and light. So this is a very controversial paper of in the 1997, the group of Adelijn Dijks in the Netherlands, where they claimed to observe localization of light, and however they claimed to achieve a very strongly scattering regime where KL is almost satisfying the Hegel criterion, as I told you, KL of the other 1.5. However, in this case, now everyone in the community agrees that absorption plays a very important role, so that what they observed, which is exponential decay of the transmission, was actually spoiled by the presence of absorption, right? So this is now established that in this experiment there's no one's localization of light in 3D, right? However, in low dimensions such as in 1D, localization have been observed in the microwave regime, such as in these experiments of Azigenak in New York, where they observed Anderson localization in this in waveguides. So we have a luminous spheres here, and here what they measure is transmission. And in this experiment in particular, they have put in evidence the importance of fluctuations that are expected to be enhanced at this in the localized regime, so that they have established the criterion for a localization of classical waves that takes into account this enhancement of fluctuations, and this is the signature of Anderson localization, right? And so another important achievement, experimental achievement, is the observation of Anderson localization for acoustic waves, ultrasound. And this experiment has been done in the group of John Page in Canada, and also had theoretical support by Sergei Skipetrov and Bart van Tiegelen in France. And this is the system the experimental setup they considered, which actually is a collection of illuminate beads, and they were able to observe this transition from diffusion to localization 3D for the first time for ultrasound. Okay, and so this is a typical mode, a typical representation of distribution of the field, both in the diffusive regime where the wave function is extended, and here and also in the localized regime where we have this well concentrated peaks of intensity. And also they see that this show up in transport as well. Is there a question? I have some.
Yes. Yes. Because I guess if I'm getting correctly, I guess you said that Anderson localization of light or Anderson localization is not going to be observed in when we consider the waves as classical waves, right?
No. The point is, so far is, well, I will talk about the major difficulty of observing Anderson localization of light in 3D, right? But here is for acoustic waves, this has been unambiguously observed, right? As this experiment nicely showed, there is no fundamental limitation to observe Anderson localization for classical waves in 3D, right? It's difficult, but it's not impossible, right?
Okay, and here acoustic waves are like classical.
Yeah, of course. Acoustic waves are classical, but for light, there is an important complication, which is dipole-dipole interactions have very high concentration of scatters that may prevent localization of light. I will discuss this later, right? But for acoustic wave, for in general, for classical waves, there is no mechanism, physical mechanism that prevents localization in general.
Okay.
Okay. Right. Okay. So
about the 1D case of GENAC, which kind of fluctuations did they monitor?
Yeah, this is very important. Yeah, the fluctuations are of transmission, right? So this quantity here is related to fluctuations of transmission. What they measure in these experiments is transmission of microwaves, and they establish a criterion based on the fluctuations of transmission. Right. This is,
Thank you.
This is very important. Yeah. Okay. Well, another very important achievement in this field is the observation of undersoil localization in 1D for matter waves. So this has been done in the group of Alain Specht in France, where they observed undersoil localization for Bose-Einstein condensate that is subjected to a random potential of produced by a speckle pattern. So this means a laser with fluctuations, and what they observed is that the propagation of the wave function that describes the Bose-Einstein condensate is localized due to disorder produced by this random field, random potential. And this is a pictorial view of this effect, and this has been observed in a waveguide very clearly that the wave function is localized in space, as is shown here, right? Okay, there are also important experiments in the group of Georg Mahet in Germany, where they claimed that they observed the threshold for localization of light in 3D, right? So this is an important experiment, but again, this is not. They agree now that this is not the transition of undersoil localization. So the conclusion that so far there's no clear experiment demonstrating undersoil localization of light in 3D. This is the community agrees on that. Okay. And there is an also important theoretical paper in the 80s by Sajid John. Where they predicted undersoil localization of light in 3D photonic band gap materials, which are materials that exhibit photonic frequency gap here. So they predicted that this undersoil localization can occur in the vicinities of this gap, but this has never been achieved so far in 3D as well. Okay, and now we will discuss an important work on the field of undersoil localization that probably explains why observing undersoil localization of light in 3D is so difficult, right? So as I told you, there are many. There have been many a lot of works of highly motivated, highly funded groups, such as the group of Adeline Lagendijk in the Netherlands, Georg Mahet in Germany, but they have never observed undersoil localization. So the question is why? The question is, this can indeed be observed. So this is the important question. And there's an important theoretical work due to Sergei Petrov in France, where they concluded that undersoil localization of light, at least for point dipoles. So this means that the scatters are electric dipoles. So this probably will be impossible due to the important role played by dipole interactions that occurs whenever you have a very strongly scattering medium, right? So this may prevent undersoil localization in 3D. So this is the subject of this paper, what they call a red light for undersoil localization. So probably this has never been achieved because it is prevented by these dipole interactions in 3D. Okay. Okay. So now probably there are some advances of trying to with the advent of metamaterials. Several groups are trying to observe this in different random structures, such as what we call hyper-uniform structures. That's still random systems, but however they are highly correlated. So such as these structures that have been fabricated in the group of Frank Scheffel in Switzerland, and actually they are so these systems are promising in the sense that probably this system can support Anderson localization, but there is no experimental clear experimental observation of this transition in this kind of structures. However, there are important theoretical predictions of like localization such as structures. So this is the work of Felipe Pinheiro and also Frank Scheffel in Switzerland, right? Okay. So now I will just summarize some of the important achievements in the field of Anderson localization, that has now more than 50 years old, and so here is in the 60s the establishment of the UFSCar Colloquium, and also so this is the year 77 where when Anderson received his Nobel Prize. So this is a very important contribution, as I told you, the establishment of the scaling theory for Anderson localization, and well, in the 80s, with the advent of mesoscopic systems, there have been experimental progress in the field of a weak localization that can be could be understood as a precursor of Anderson localization, and so this has been observed for light in the 80s. So there is the theory of white paint by Anderson in 86, and so in the same the 80s also a lot of progress, numerical progress in the description of Anderson localization due to Costa-Tsoukalos, Schreiber. So these are indignities that are very important to understand Anderson localization, using numerical more sophisticated numerical models to probe Anderson localization. And there is a very interesting but rather provocative work by Suya in '87 that he claimed that at that time that localization, Anderson localization of gravitational waves could prevent its observation. So this is something very provocative at the time, but I'd like to quote this here. And also the work of Sajid John in the '88, and also important progress in the random matrix theory that has been applied to the study of Anderson localization. Well, here in 1997, this experiment that I told you on the first claim of observation of Anderson localization 3D, that we now know this is not established, and in the 90s, important progress in the field of random lasing, that is an important application of localization, if you wish, that we can produce lasing in a random system where disorder, where multiple scattering plays the role of the mirrors in the conventional laser. And well, and here so I will not go through all the points here, but I would just try to list some of the important contributions in this field. And so this is the observation of Anderson localization in the ultrasound regime for ultrasound that I mentioned here. In 2008, the observation of Anderson localization for bullseye condensates, and also the work by Sergei Skipetrov in 2014, that is for red light, for instance, localization, for point dipoles in 3D. And what's next? So there probably I would like to list some of the important perspectives that this field still has, and one of them is certainly localization of light by cold atoms. And so here the Romain Bachelard is working very hard on the theoretical side of this problem, how to observe or to predict undersea localization of light for cold atoms. In the experimental side, there's the very nice work in the group of Robin Kaiser in France, who is trying to very hard to observe clear manifestations of undersea localization of light in cold atoms, right? And another important, still open question is whether or not one can localize seismic waves in the Earth crust, right? So there are also experiments, ongoing experiments in France that are trying to observe this phenomenon in the crust, and also the possibility of observing localization of gravitational waves. This is that this has been done, is being currently investigated with the vehicle collaboration. And also, as I told you, in the case of the hyperuniform metamaterials, there's the quest of localization of light in metamaterials. One of them is the hyperuniform case that I mentioned. So I will now concentrate on that, right? Is it possible to observe undersea localization, light localization in metamaterials? This will be the topic of the rest of this talk that we'll discuss. Okay. Well, so I will just briefly mention the first work that I have done in this field, and that is very simple in 1D. So the idea is to combine a metamaterial, in this case, that has negative refraction with in the random fashion in 1D. And what we have demonstrated in this work is that suppression of undersea localization in 1D is possible, but only for very specific frequency region, which is related to the Brewster anomalies. I'm not going to describe in details this, but this is the first work that I have done in this field of undersea localization of light, to begin with, in a low dimensions, in 1D in this case. Well, now I will focus on a different kind of system, this different kind of metamaterial that of course does not exist in nature, but however they are inspired by nature, right? So this is what they call a Vogel spiral, for instance. So this has been actually first fabricated and proposed in the group of Luca Del Negro in Boston University. And so this is the distribution of the scatters in the plane on silicon. And so this has been inspired, as I said, by nature as the distribution of seeds of the sunflower, right? And here, this field of biology is very old, and this is what we call phyllotaxis, that from the Greek phylum, that means leaf, and taxis, arrangement. So they were able to fabricate these photonic structures inspired by natural structures such as the sunflower. And this, as I said, this field of biology is very old, since one can trace back this to the work of Leonardo da Vinci, Kepler, and Auguste and Louis Braguet. And this is a very important source of inspiration to the development of new photonic structures. As I said, this has been first proposed by Luca Del Negro in Boston, right? So the point here is that these structures, what we call Vogel spirals, are generated by very simple mathematical rules. So here we show this in polar coordinates here. So this is given, the angle is given by what we call the divergence angle, which in this case is proportional to the golden number that also occurs in different systems in nature, right? This is what we call the golden mean. And this has been used here to fabricate these Vogel spirals. And the point is that by changing this parameter, this angle, one can produce different structures with different degrees of correlation, right? So, the point is, the systems are not random, right? They are deterministic, as this is very clear from these formulas here, but they can support strongly scattering and also localization. I will discuss in the following. Is there a question?
Yes.
Yeah,
Sorry, I didn't get that. What are these picture like? This is SEM of what? This is SEM of material or?
yeah. These are micropyramids of silicon, as shown here, right?
Okay.
And so this is imaging of these structures that have been fabricated to investigate light propagation and diffusion, right? So this is a picture of these structures that have been fabricated, right? And these structures, they have unusual properties that can only be occur here. That so this means that they cannot occur in random systems, and also cannot occur in periodic systems, photonic crystals. So so I will discuss here, as I told you. So one can vary this angle, what we call divergence angle, to produce different degrees of correlation between the position of scatters, and we call this we call this tau spiral, pi spiral, mi spiral. The only difference is the angle, and if you calculate the diffraction pattern, you see that the diffraction pattern is completely different depending of this angle. So, yeah, please. Yeah.
Then I'm a bit confused about this angle. That this is the angle. This is the direction of.
This is the positions of the scatters in this plane, right? Given in polar coordinates. So this angle is just a system parameter that can be controlled or varied, right? So, this angle it can be proportional to the golden number. So this generates what we call the Vogel spiral, the golden angle Vogel spiral. Okay, so these are system parameters that one can vary and produce different physical properties depending on this angle. Now, this is just a mathematical rule, deterministic mathematical rule to generate these structures, right? They are very simple, right? And so, of course, if you want to do applications, this is much simpler than exploiting random structures, because there is no simple, they are not in principle reproducible in the random case. And here, of course, they are, because they are very simple mathematical rules. Of course, always subjected to randomness that are intrinsic to the fabrication process. So, okay. So here, as I told you, we can construct different structures with different degrees of correlation in these. We call it different degrees of order, if you wish, right? Just by yeah, please.
Excuse me. Is the thermodynamic limit of this system well defined, in the sense that when I increase the system size, do I always get the same scattering properties after some given length?
Yeah, this is a very important question, and so here, as the system is not random, right? We cannot establish what is typical for the random case, which is self-averaging, right? So this is, I think that the correct answer to your question is in order to see whether or not this is what is the behavior in the thermodynamic limit, one should verify the self-averaging property. That is not that does not apply here, right? So okay, but of course the system depends on the system's the physical properties will in general depend on the system size, right? As I will show you in a specific example of localization. But in principle, we cannot establish a self-averaging procedure here. Right.
Okay, yeah, I was asking because you can see, for example, in the pi spiral, that's the distance between the different kind of circular layers changes with the distance to the center. So this is why I wonder, yeah, when you increase the system. But okay, let's use the example. Thank you.
Yeah. I will discuss this behavior in the specific case of light localization. How the physical properties depends on the system size. Okay. So as I told you, this could be these systems could be seen as a hybrid structure between random and periodic photonic structures. So they show unusual optical properties, as I told you, that cannot be found in either random or periodic structures. One of them is the multifractal local density of states. As you can see here, there's a multifractal distribution of band edge states. So here is a photonic band gap that also occurs in photonic crystals, and so we have a multifractal distribution of these modes here. So they have extremely rich mode spectra, and also an important property is that light scattering by these structures encodes a very well-defined sequencing of orbital angular momentum, and also they exhibit polarization insensitive scattering of light. So with different qualitative factors, with modes with different lifetimes, if you wish. Okay. So the point here is that we shall investigate light propagation in these structures using what we call the Green's matrix method, which is very well known, very well applied in the field of random medium, right? Light propagation in random medium, and the only approximation is in this model is deals with the single scattering. So the only approximation is that each scatter is a dipole, and so that we can construct or compute the field as the sum of the incident field and the field that is multiply scattered by all other dipoles. So G is the Green's matrix, and T is the scattering matrix that describes scattering properties of single dipole. Right? So the important thing here is that all multiple scattering orders are taken into account. Okay, so this has been extensively used in the field of Anderson localization. There are several works on that, and also this model is excellent to describe light propagation in cold atomic gases. So as you know, atoms are perfect dipoles, so this model is perfect in this sense. So there are important works in this direction, including the group of Romain Bachelard as well, and together with Robin Kaiser in this field. Okay, and also in Brundle lasers. So what we will use this methodology that is known in the field of light propagation in random media to the aperiodic case as well. Okay, so this is just a computation of the decay rates of light propagation in a random medium, where we using this method to establish that for strongly scattering systems, one has this characteristic Power law decay for the decay rates in 3 dimensions. Okay, just an application. And The idea here, the all calculation boils down in diagonalizing the Green's function, both in the scalar approximation and the vectorial case, where we take into account polarization effects. Right. So this matrix describes light propagation or wave propagation in between two point scatters, right, located at positions N and M, right? And this has been this matrix. Of course, the system is open, so their eigenvalues are complex. So the system is no emission, and so we have to investigate the behavior, or the real and imaginary part of this, the eigenvalues of this matrix, right? And so the important thing here that one can extract information about the decay rates and the positions in frequency of this matrix to compute, right? To compute important physical quantities to study light propagation in such structures. So here I will discuss the Thouless conductance for light. That is as I told you, is a very important criterion for the description of undersea localization in open systems. So so here what we have is in a situation where the system is localized, we have the spectrum of the system. So we have several modes with a given width, which is inversely proportional to the decay rate of the mode, and we have the separation here, delta omega, and these quantities can be obtained by the real and the imaginary part of the eigenvalues of this green matrix, right? And on the other hand, we have here the situation where where there is diffusion, and here we have a strong modal overlap in between the modes of the system. And one can define a quantity which is what we call the Thouless parameter, which is the ratio between the level width over the level spacing. And by looking at this pictures here, we can see that in the localized case, G is less than 1. So the modes are very well localized, right? So we don't have a very strong modal overlap in the localized case, whereas in the diffusive case, we have a strong overlap, so that this quantity is larger than 1. So this establishes the Thouless criteria for localization, so that G, when G is larger than 1, when one has diffusion, and when G is smaller than 1, one has localization. Okay. And another important quantity that we should look at is the degree of spatial localization of optical resonances. So this is given by the IPR, right, which is the inverse participation ratio. And so if IPR is 1, so the system is localized. Whenever IPR is, if the system is diffusive, so the wave functions are extended, and IPR goes as 1 over n. And whenever the wave function is localized for over only two scatters, the IPR is 1/2. But of course, this has nothing to do under localization. This is a collective effect that is related to sub and super regions, right? So the point here is that one can relate the decay rates, the widths of the eigenvalues of the Green's matrix to the relative widths and positions of the quasimodes. Okay, so this is the important physical information that one can obtain using this method, right? The positions and in frequency and the decay rates of the modes. And here, just to exemplify, we see the distribution of the decay rates here and the energy of the modes in the random case, where we have a random distribution of dipoles in a plane. And we can see here that in the random case, we have a branch, we have a band of proximity resonances, a collective modes that involve typically two scatters that has nothing to do with Anderson localization, but that shows up here. Okay. Here we compare the random case that I showed before to the case where the scatters are distributed according along the golden angle Vogel spiral, and we can see immediately that this band of proximity resonance that are related to sub and superradiance are not present in the periodic case, due to the completely different distribution of scatters in the space, in the plane. So that this prevents the occurrence of this collective modes in the periodic case. Okay, so this is one important conclusion. And now what we do is, using this Green's matrix method, we can compute the Thouless conductance that I explained before for the golden angle Vogel spiral. So we have here 2000 electrodipoles distributed in a golden angle Vogel spiral, and we can compute the Thouless conductance as a function of frequency for two different optical densities. So this is what controls the strength of scattering in this system. So here we have one scatter per wavelength cubed, and here we have 15 scatters per wavelength cubed. And we can see that for certain frequencies, we have a band of localized states for higher optical densities that suggests the appearance of a band of localized states, right? Of localization in this case. So it's important to emphasize that here we don't have Anderson localization, because the system is not random by definition, but we are using established concepts for random systems to the periodic case. But this is what all that we know, right? We have no established concepts in the field of light propagation in random systems that they are just using here, and to probe this different light localization transition that is expected to occur here, as this result show. Okay, and we can also, for the whole family of Vogel spirals with different diverse angles, we can establish the diffusion localization threshold, which is given by these lines here that are related to this equation, that the log of g is equals to 0, g is 1, right? And we can establish that in this case, the critical condition for a light localization transition in this case is around 3.5. So this is the critical value for the optical density for all the spirals that we have investigated here. Okay. Yeah.
Excuse me.
Yeah, please.
In the previous slides, you showed the light. Yes, here you showed that you have localized light.
Yeah.
What would be a sign that you could see under the specific localization, Anderson localization?
Yeah. So I just want to make clear that this is not Anderson localization, because the system is not random. This is very important, right? The system is deterministic. There is no randomness here. So this is an important point. What we are, as I told you, what we are doing is to borrowing concepts of Anderson localization and applying them to this transition that we are reporting here, right? So am I clear? This is not Anderson localization because the system is not random by definition.
Okay.
So
but Felipe, sorry. But then you define, for example, a conductance. But your system is, I mean, being aperiodic, you have a strong, how to say, for example, even the density changes with the radius, for example.
Yes.
And my question is, how much sense does it make to compute a conductance based on the eigenvalues, knowing that when you move in the system, the properties changes significantly? For me, this conductance story is kind of average value that would work if the system is more or less the same everywhere, up to disorder, of course. But here, when you move in your system...
You mean homogeneous?
Yes, homogeneous, exactly. I mean, even if you had a disordered but inhomogeneous density, the concept gets a bit weaker. Do you agree, or?
Well, whenever we have a spectrum of modes, when you can define the Thouless conductance is all about modal overlap, and this, in principle, can be applied for random, uniform random, or aperiodic structures. There is nothing fundamental that prevents one to investigate modal overlap in an aperiodic structure or a random structure, right? So this is my point. Okay.
Okay. Yes, and I guess it's more the term conductance that I think is maybe a bit less. But no. Okay, I agree, Jen. I agree. Yeah.
I mean, this is maybe this is the traditional term, but what we are measuring here or computing here is the degree of modal overlap. So in the end, this is what is important for transport.
Yes, I agree.
No matter if this is random, uniform random, or aperiodic. Okay, so again, what we are doing here is trying to apply scaling theory, which is a great principle for Anderson localization that I explained in the beginning of the talk, to this case. So here, what we do is to investigate how the system. This is also related to the question that Romain mentioned before, that how the system evolves as one increases the system size. So this is the essence. This is the topic that is covered by scaling theory. And just briefly review this, that the main idea is to study how the conductance evolves with the system size. And if the modes are extended, the conductance grows with the system size. So if you increase the radius of the structure. However, if the modes are localized, the G decreases with the system size. And at the critical point, the conductance is independent of the system size. And this information is captured in this scaling, the single parameter scaling hypothesis, in this logarithmic derivative of the conductance. And here we see that by plotting this quantity, we see that transition, at least for the random case, can only occur in 3D. And in 1D and 2D, the system is always localized. Of course, it can be larger than the system size, can be smaller than the localization length, but in principle, all the states are localized in this low dimensional case. And of course, what we will do now is again to investigate how the conductance as that is defined as a degree of modal overlap behaves as one increases the system size. And this is what we do here. So this is the beta function defined in this equation for whole family of Vogel spirals with different divergence angles, the golden angle, the tau, the pi, and the mu, for different system sizes. The different colors here are different system sizes, right? For what we are increasing the radius of the plane that supports this this structure, and we can clearly see that there is a transition from localization to diffusion for all structures that we have investigated, right? And this agrees with this great principle of Anderson localization, that is scaling theory. Again, that has been developed for the random case that we are applying here, right? So apparently, this transition that we have discovered shares some common features with the Anderson transition. But however, it's not Anderson transition because, again, the system is deterministic and not random. Okay. Well, I don't think I have much time, right? How much time do I have, Homa?
Well, now it's been 1 hour.
Okay.
How long do you need?
I will conclude. I will skip this. What we have done is just to again to understand the whole of the far field and the near field effects in this problem. But I will skip all this details. I would just like to mention that we have an ongoing collaboration on the experimental side. So this is in collaboration with Lucas Sapienza, University of Southampton in England, where what they do is to fabricate these structures and embed in this Vogel spirals quantum emitters, right? Quantum dots that emit light, and what they can measure is the lifetimes of these modes, and so this is related to the quality factor of the modes. So one can extract their lifetimes here as the width of half maximum of this resonances, and then study the statistics. So this is statistics of the quality factors of these structures, and compared to simulations, because there's an important prediction that in the localized regime, the distribution of quality factors is log normal, and we are investigating the distribution of quality factors to see some evidence or some signature of localization in this case. And in the recent publication, what we observe is the distribution of the model structure. This is actually an image of the mode that of the different modes can be supported by these structures, and we can see there is a very rich model structure in this Vogel spirals that, well, we can compare this to numerical simulations, and of course this very rich model structure lead to very different transport properties, right? That show up in an experiment. So again, these are images of the mode obtained by embedding indium arsenide single quantum dots in the structure, right? Okay, so I guess I have no more extra time, so I will just conclude by saying that, again, Anderson localization has a rich story and still reveals surprises. And I focused here specifically in investigate localization, light localization in metamaterials. So specifically in Vogel spirals, that are structures that are inspired by nature, and we discovered in this kind of structures a new type of light localization transition that is not Anderson. Again, because the system is not disordered. It's just is deterministic. And however, this light localization transition shares some properties with localization, such as absence of level repulsion. I did not discuss it in details, but I did discuss the behavior of the Thouless conductance as a function of the system size, which is the basis of a scaling theory for localization. And I briefly showed some experimental results of mode imaging. And for further reference, this is the paper that they discussed it in more details here. But there are other references, including on the topic, including review paper, if you want to know more. So with this, I'd like to thank for your attention, and also the supporting agencies CAPES, NVQ, FAPERJ, and the British Royal Society. Thank you.
Thank you very much, Felipe, for this nice colloquium. Are there some questions? Can you see the chat, Felipe?
I will stop my presentation and.
Okay. Otherwise, I can read it.
Yeah.
No, on the top right.
Okay. There's a question by How. Okay. The question is, can these spirals show long range or even infinite order in the spatial color? Yeah, they can show you. This is a good question. They can show long range correlations, and this crucially depends on the angle, right? If you vary this angle that gives the distribution of scatters in the plane, they can show different degrees of spatial correlation. So, for instance, there is, I will show again the presentation here. Okay, if you go here. Okay, so in the sense that what is different is the degree of correlation is smaller in this case, what we call the pi spiral, in comparison to what we say the more ordered structure is the tau spiral. Okay, so again, the degree of spatial correlation depends on this angle in this kind of structures. Okay.
Are there other questions?
No, infinite, no. I mean, yeah, we can vary them, but they are not infinite, right?
Okay. Felipe, I'm curious. This work on quantum dots. How many dots are they able to put together? Dozens, hundreds?
No, this is a very good question. But the point here is that Lucas Sapienza was able to probe a single one. You can have the ability of to probe a single one, and this is what the differential of this experimental study, right? Usually we put a lot, but we can excite a single one, right?
Yes.
A single quantum dot.
But then he is able to construct an array of dots, right? Or is the idea to work with a single dot?
The point is that he can probe, construct an array such that the spiral is localized in the region of a single one. So actually, what we do is to probe a single quantum emission, single dot quantum emission. This is the point.
Ah, okay. But the light fills the spiral.
Exactly. So actually, the quantum dots are embedded below the structure, right? We excite and see the emission of a single quantum dot. This is the important point.